Hello class, in this video we're going to be looking at electron shells and the Bohr model. The learning intention of this video is for us to quickly explore the energy levels for each electron shell, for us to explore the maximum capacity of electrons that can fit in each shell, and lastly for us to learn how to illustrate the structure of an atom diagrammatically. So the first point of discussion is talking about what are electron shells and the energies associated with an electron shell. We know that electrons are not randomly scattered around the nucleus and that these electrons belong in their respective electron shells. So they still move, but they only move inside of their electron shell. And what I need you to understand is that each electron shell has a different energy level associated with them. Let's talk about this in a bit more detail. So let's now talk about energy levels of electrons. The amount of energy that an electron possesses will depend on which shell it's located in. I'm going to use an stereotype to help you understand. Based on some stereotypes as well as your own personal experience, where do you typically expect to find engaged students versus disengaged students in the classroom relative to the teacher? So what that means is, do you expect to see engaged kids sitting closer to the teacher or away from the teacher in the classroom? In this analogy that I'm using, I'm considering the students to be electrons and the teacher to be the nucleus. Stereotypically, we often find disengaged students sitting at the back of the class, so sitting away from the teacher, whereas the engaged students are more closer towards the teacher. So how does this relate to the energies of an atom? Well, in terms of energy, electrons found closer to the nucleus have low energy. Similarly, engaged students are more well-behaved and have lower energy and thus are closer to the teacher or to the nucleus. So in this example on the right-hand side, electrons found in the first shell will have very low energy compared to the electrons found in further electron shells. In contrast, the electrons that are found further away from the nucleus tend to have a lot more higher energy. Similarly, if we were using the analogy, disengaged students tend to have a lot more energy, a lot more disruptive energy, and thus are situated and positioned away from the teacher. Have a go with answering this question. This question wants you to compare the energy levels of a valence electron compared to electrons found in the inner shell. The answer to this question is that valence electrons will have greater energy compared to electrons found in the first shell. Let's now talk about how many electrons can fit in each shell. So the number of electrons that an electron shell can hold will vary. So let's look at these elements down below over here. Using this example, what is the maximum number of electrons that can fit in the first shell? In this example, we can clearly see that only 2 electrons can fit in the first shell. Use the following atomic structure of these elements to identify what is the maximum number of electrons that can fit in the second electron shell. The answer to this is going to be 8, so we can clearly see that by the element neon and all the other period 3 elements. There is an easy way for us to remember how many electrons can fit in each shell, and that's given by this particular formula over here. So the maximum number of electrons is equal to 2n squared, where the letter n corresponds to the electron shell that we're interested in. This diagram over here already tells us how many electrons, what's the maximum number of electrons that can fit in each shell, but let's verify this using the formula. So if you want to find out how many electrons that can fit in the first shell, we sub in n is equal to 1. So 1 squared is equal to 1, and 2 times 1 is equal to 2. And again, that is supported by this diagram. If you want to find out how many electrons that can fit in the second shell, you sub in n is equal to 2. 2 squared is 4, 4 times 2 is 8, so you should have 8 electrons. And similarly, you do the same thing for the third shell and fourth shell. What I do want to emphasize is that although that the third shell can hold up to 18 electrons, for the purposes of our year 10 chemistry subject, let's say that only 8 electrons can fit in the third shell. The reason why this is the case is that in year 10, we are only interested in the first 20 elements of the periodic table. And as a result of this, you can't actually have 18 electrons on its last shell. So for the third shell and the fourth shell, for this particular subject, let's assume only 8 electrons can fit in those shells. Have a go with answering this question. This question wants you to find out what is the maximum number of electrons that can fit in this second shell. So if you were using this formula over here, substitute n is equal to 2. So if you do that, you should therefore get an answer of 8 electrons. We're now going to look at how do we draw and illustrate the atomic structure of an element. So the Bohr diagram is essentially a way for us to represent atoms, and there are a few rules that we need to understand. The first rule says chemical symbols should always represent the nucleus of an atom. So you put that at the center as shown over here. Now, when we start to fill up the electrons in each shell, we always fill in electron shells that are closest to the nucleus first. So starting from the lowest energy, then moving away to high energy levels. In the very first electron shell, there is one coordination site as shown over here. Each coordination site can only hold up to 2 electrons each, so you draw therefore the first 2 electrons next to each other like so. In contrast, the second and third electron shell has 4 coordination sites each, as shown over here. Remember, again, each coordination site can hold up to 2 electrons, so as you can see, the second shell and the third shell can hold up to 8 electrons in total. Please note that the first 2 electrons in the first shell, they should always be paired when you draw them. So let's use oxygen as an example. Oxygen has an atomic number of 8, so it should have 8 electrons. So the first 2 electrons in the first shell should be paired as illustrated over here. When we start to fill in electrons in the second and third shell, please remember that each coordination site needs to be partially occupied before you pair them together. In other words, what that means is, please start to add electrons in a clockwise manner, and once all of the coordination sites are partially filled, then you can start pairing up the electrons together. So let's look at oxygen. We know that oxygen has 8 electrons. We currently have used 2 electrons. So therefore, there should be 6 electrons left, and this should be represented in the second shell. So if I was to follow what this dot point says, let's add electrons in a clockwise manner. So you go 1, 2, 3, 4. And once we've occupied each coordination site, then you may start pairing up of the electrons. So you put the remaining 2 like so. The reason why we need to partially fill in each coordination site is because we generally don't want the electrons next to each other, because if they're next to each other, 2 negative charges causes electrostatic repulsion, making it unstable. Let me show you some mistakes that I often see when students draw Bohr diagrams. So the first mistake is that students often not pair the first 2 electrons together. Remember that the first shell has 1 coordination site, so therefore these electrons need to be paired up in the first shell. The second mistake that I often say is that when you draw electrons in the second and third shell, students often pair these electrons before each coordination site is partially filled. So if you look at this example over here, we know that carbon should have 4 valence electrons, but these students have grouped these electrons together instead of occupying each coordination site. So if you were to actually draw the correct Bohr diagram of carbon, the electrons should fill up each coordination site instead, like this. By now, you should be able to draw all elements in the Bohr model. So I want you to please answer this question. Which of the following is the correct Bohr model for nitrogen? If you examine both of these options over here, both of them have the exact same number of electrons, and they also have the exact same number of valence electrons. However, option B is going to be correct, and the reason why option A is incorrect is because they started to pair up the electrons before occupying all coordination sites. What I'd like you to do now is I want you to please pause this video right here and draw the Bohr diagrams for both phosphorus and aluminium. To draw the Bohr diagram of phosphorus, it's useful to find out how many electrons it has. So it has 15 electrons, and it's also useful to find out how many valence electrons it has. So phosphorus is found in group 5 or group 15, and so therefore it should have 5 outer shell electrons. Let's use this information to now draw the Bohr diagram of phosphorus. So you always draw the first 2 electrons paired in the first shell like so. Once we've filled in the first shell, we start to fill in the second shell by occupying each coordination site, and then we can start to pair up the electrons together. So in doing so, at the moment, I've got 10 electrons. I need to have 5 more electrons. So to draw the 5 electrons, I occupy each coordination site, and for the last one, I pair them together. So this is the Bohr diagram of phosphorus. Similarly, we'll find out how many electrons aluminium has. It has 13 electrons, and it's found in group 3, so therefore it's got 3 valence electrons. So we draw the first 2 electrons in the first shell. We then start to fill in the second shell like so. And if we've got any remaining electrons, we fill it in the third shell by occupying each coordination site. And as you can see, it has 13 electrons, and we could also see that it has 3 valence electrons. For the next question, I would like you to now have a go drawing the Bohr diagrams for the following ions. To find out how many electrons are present in Mg2+, Find out how many electrons are present in the neutral magnesium atom. Neutral magnesium contains 12 electrons, and this 2 plus sign over here indicates that it's lost 2 electrons to become an ion. So as a result, it's got 10 electrons. So if we were to draw the Bohr diagram of magnesium, this is what the Bohr diagram of magnesium ion should look like. And as you can see from this example, we can see that magnesium doesn't actually require that third electron shell at all. For oxygen, oxygen has 8 electrons for the neutral atom. The -2 sign over here indicates that oxygen has gained 2 electrons, so therefore it's also got 10 electrons. So if you were to draw the Bohr diagram of oxygen, notice that the Bohr diagram of oxygen is actually identical to the Bohr diagram of magnesium ion as well. What I'd like you to do is I'd like you to have some practice drawing the Bohr diagrams for the following atoms and ions. This is the end of the video. Thank you for watching, and I'll see you guys again in the next one. Bye.